ISAS-SISSA, Trieste. Yeah.
Para o nosso colega do CBPF, o professor Antony Valentini. He did his PhD in Sissa, Italy, with Dennis Sciamma, which was the advisor of Hawking also. And then he was professor in Clemson University. Now he's in Imperial College. He stayed many years in Perimeter Institute. And he has been working in many subjects concerning quantum foundations, concerning the Broglie-Bohm theory and extensions of quantum mechanics, which is very, very interesting papers and subjects, and he'll talk to us this day. So thank you very much, Antony.
Thank you, Nelson. Thank you. It's a pleasure to be here. I think it's quite some years ago that I visited. Wait for Nelson to sit down. Are you going to stand up, or are you? Now, you're not going to interrupt me too often, right? Okay. All right. Okay. Okay. Got him under control. All right. So, whoops. My subject is beyond quantum mechanics. There's one idea, really, I want to convince you of, which I can summarize in one slide. The idea is that quantum theory is a special case of a much wider physics. We inhabit a small region of possibilities. We think that quantum mechanics is fundamental, but it is not. According to quantum mechanics, at least statistically, the universe is local. You can't signal non-locally. The uncertainty principle is always valid. There are limits on what you can measure. And in particular, the Born probability rule is a law of nature. You look in any textbook, it tells you the Born probability rule is a fundamental law of physics. My claim is that actually this is not true. This is actually just a certain special state, a state of statistical equilibrium that we happen to be living in. That in principle, there exists a wider physics in which the Born rule is violated, in which non-locality can be controlled and used for superluminal signaling. And it is a deterministic theory where the uncertainty principle can be violated. Now, those are big claims, but that is the gist. And I'm going to try and explain to you, part of the talk is going to be about explaining, well, why are we stuck in this region? And the idea is that there is a process of dynamical relaxation, a little bit like thermal relaxation. There's a broad analogy with thermal relaxation, though there are differences. And also, I'm going to try and talk a bit about how we might escape from this region and see evidence for this broader physics. And then finally, I'll talk a little bit about what would this new physics be like, how we could access it, and what we could actually do. So, the story begins in 1927 at the Solvay conference, where Louis de Broglie presented his pilot wave theory of a many-body system. There's a lot of mythology and misconceptions about what happened at this conference. If you want to know the truth, here's the book you need. I spent 10 years or more actually studying the proceedings of the fifth Solvay conference. Was published in French in 1928. I don't think many historians read them carefully. This book contains a complete translation of the proceedings into English with lots of commentary and analysis. The parts that I wrote, particularly focusing on de Broglie, and in the period of 1920s, de Broglie developed, people don't really know this, they think that de Broglie just extended wave-particle duality from photons to massive particles. That was just a byproduct. What de Broglie was really doing is developing a new non-Newtonian form of dynamics. Now, here is what he presented at the fifth Solvay conference. It's a dynamics of a many-body, low-energy system of spinless particles. you have the usual many-body Schrödinger equation for a wave, which in this theory is not a probability wave. It's a wave that guides the motion of the particles in accordance with this law of motion that de Broglie postulated. It's a law of motion for velocity. So when I say it's a non-Newtonian theory, I mean it's a dynamics not for accelerations. There's not a law of motion for acceleration. There's a law of motion for velocity, which is given by the gradient of the phase of the wave function, where the wave function is a complex valued field on configuration space that guides the trajectory of the system. All right. Now, an example, the two-slit experiment. There you just have a wave in three-dimensional space. The law of motion looks like this. If I have an incoming plane wave, if you solve this equation for the trajectory, you get something that looks like this. The particle will start somewhere here, it will wiggle a bit, and it will end up somewhere. Now, this is postulated to be true, even if in practice you don't know the initial position. This is just a theory that is just postulated, okay? Now, so an individual system is described by both the configuration and the wave. The wave has no a priori connection with probability. It determines the motion of an individual system. Now, if we consider an ensemble of systems with the same wave function and different starting positions, so here it starts here, maybe instead it could start here, it could start here, it could start there. We have an ensemble distribution of configurations. If you assume that the initial distribution is given by the Born rule, then you recover quantum mechanics. And this was shown fully by Bohm in 1952. Now, let me just illustrate for one particle. One particle's Schrödinger equation implies this continuity equation for psi squared. Remember, psi squared is not a probability. It's just a wave. Psi squared is just the amplitude squared of this wave. Excuse me. So, now de Broglie postulates that in addition to the wave, there is a particle following this law of motion. Let's apply that to an ensemble. Imagine I have an ensemble of systems where each system has the same wave function, but the initial position can differ from one system to another. And I'm going to assume that each system moves according to this velocity. So by construction, the distribution of positions obeys this continuity equation, which just says the particles are moving with this velocity. But rho could be, is arbitrary. It could be anything. It doesn't have to be psi squared. Now we have a simple theorem. You see that rho and psi squared obey the same partial differential equation. There's a simple theorem that if they're initially equal, then they're always equal. Okay, this is quantum equilibrium. So psi squared is an equilibrium state. Once you're there, you stay there. Now, this reasoning generalizes for a system with a general configuration. Imagine I have a system with a configuration Q and a wave function. This could be T here. For those who like cosmology and so on, you could be, if I'm on a curved space-time, a classical curved space-time background that is globally hyperbolic, I can foliate it by space-like hypersurfaces that I label by T. Q here could be field configurations on that hypersurface. So this would really be a wave functional, and this would really be a functional Schrödinger equation. You have the same kind of thing. Okay, you have a Schrödinger current in configuration space. I can define this velocity field, and by construction, an arbitrary distribution will obey this continuity equation, which is the same as the continuity equation for psi squared. So on this hypersurface, the probability distribution for quantum fields, for example, will also be preserved in time. Once you have the Born rule, you stay there. All right, so now let's look at go back to the example of the two-slit experiment. If I have a quantum equilibrium distribution in the sense that, let's say I repeat the experiment many times, and over the ensemble, the initial positions of the particles are distributed according to psi squared as you come in. that distribution is preserved in time. So the distribution of particles landing at the backstop will be psi squared by that simple equilibrium theorem. Okay. On the other hand, if you have a non-equilibrium distribution coming in, you will get a deviation from quantum mechanics. So as an extreme example, if all the particles start out close to this point, they will all land close to that point, and there will be no interference pattern, okay? Or if you think about this, if all the particles started in the top half here, they would all land in the top half here, and half of the pattern would be missing. So if you input rho not equal to psi squared, you get deviations from quantum mechanics. So what does this mean? Okay, so what I want to emphasize here is that according to this theory, quantum mechanics, I'm giving this as an illustration of the general idea, that quantum mechanics is a special case. If you take this theory seriously, it's telling you that, all right, we see this equilibrium distribution, but it didn't have to be that way. In principle, this theory says this should be possible. Okay, in principle, you can have distributions not equal to psi squared. At least that's the way I think about it. Now, some people disagree. So other workers in the field, in fact, most people, in fact, almost everybody, except me, come to think of it, insists on taking this as a postulate. Now, I think that's wrong. In fact, if you look at Bohm's original papers in 1952, Bohm didn't look at it that way. He had the idea that this was a bit like a sort of equilibrium state. So, but then he kind of changed later on. It's unfortunate, but the original Bohm, 1952, I think you had it right. So the laws of motion are postulates, okay? These are the laws of, this is a law of motion for the guiding wave. This is the law of motion for the configuration. Initial conditions are empirical, okay? If I look at Newton's law of motion, I apply it to the motion of the moon, okay? The laws of gravity and Newton's laws of motion are fixed. The initial position velocity of the moon is not given by a law. It's something empirical. It could have been different. It's a contingency. Okay, and it's the same thing here. If you look at the two-slit experiment, this example, the laws of motion that we postulate tell you the motion of an individual trajectory. The initial conditions where the particle happens to begin is not fixed by a law. It's an empirical thing. Now, so I claim that if you take this theory seriously, then quantum theory is just a special case of a wider physics. So here is quantum theory, and here is pilot wave theory. It contains quantum theory as a special case. We have the Born rule, but there's a much wider physics outside of it, which I claim we could, in principle, access. Now, you may say, well, that's all very well, but experimentally, we always see the Born rule. So here, for example, is a particle in a two-dimensional box. The wave function has been prepared to be a superposition of the first 16 energy states of the box with certain coefficients. Okay, and if you plot psi squared, this is what you see. Now, if I prepare a particle in a box with this initial wave function, and then I do it again with another particle in a similar way, I do it many times, and then I measure the positions of each particle, what will I find? If I go in the lab and I do this, I will find this distribution. And it doesn't matter when or where I do this, today, tomorrow, yesterday, in Rio, even in Rio, okay? You find this distribution, no matter how many, you know, whatever you've been drinking, Nelson. You always find this distribution. And because we always find this, it's generally seen to be, it's great to see, you know? It's great to see. It's great to be here. It's great to be here. Thanks, Nelson, for the invite. You always see this distribution. Now, why? Now, of course, most people will say, well, it's just a law of physics. There is no why. But in pilot wave theory, we can give an answer. So what happens if we take an initial distribution that is not psi squared at t is 0? What happens? We can find out how such a distribution evolves by integrating this equation. This is an equation. Remember, we said by construction, if every particle follows the de Broglie velocity field given by the gradient of the phase, any initial distribution will evolve by this continuity equation. So we can integrate. If we know the wave function, we know the velocity field, we know this v is a function of position and time. We can integrate this equation. So let's do the following numerical experiment. Here is our initial psi squared. As I said, it's a superposition of 16 modes. This, of course, evolves in time psi evolves according to the Schrödinger equation. So I have a superposition of 16 modes in the box, psi squared, it sloshes around, it evolves in time. Here's a plot. It's a periodic system. After a certain time, it evolves back to its original form. So here we've evolved the wave function over one period, okay? Now, instead of the actual distribution of particles, instead of being equal to psi squared, we're going to take it to be this. This is just a cos squared distribution. Okay, it's different. Now, notice that what we're talking about here is something that you cannot even discuss in quantum mechanics. We're doing something that is impossible to conceive in quantum mechanics. This is the initial psi squared. This is our initial probability density. It's going to evolve according to this equation. What happens? So, just to be clear, the initial density we've taken, oh, sorry, it's not a cos squared, it's a sine squared. It's actually the ground state wave function squared. The actual wave function is this, a superposition of 16 modes, the usual thing of a particle in a box, all right? So now what happens when I evolve forward in time? Over half a period, this is what you get. Over a full period, ta-da! If you look at this, it's remarkable. Look at the features that are captured. It's not 100% exact, but look how close that is. The system relaxes to equilibrium. Now, the few things to say is that we've done a bit of coarse graining here. Those of you familiar with, well, everyone's familiar with Gibbs thermal relaxation in phase space. It's quite similar to that. You get fine-grained structure on very small scales. So, for example, here, this is a tiny area, 0.006% of the area of the box. This is the actual fine-grained density. There is a crazy complicated fine-grained structure. Not surprising because the trajectories are very erratic. This is sort of plot of a trajectory that starts in the middle of the box. Okay, remember the guiding wave function is a superposition of 16 modes. Okay, the trajectory is going all over the place. And if you coarse grain, this is where you get, so you can see how you have this quite remarkable over just one period. And in fact, I might mention that when we first did these simulations, I wasn't expecting it to be as good as this for just such a simple system. In fact, the original discussion of this, I had some papers in 1991. I was talking about relaxation for a system with many particles. So you have enough complexity in the velocity field and you get relaxation, and then you would extract particles from that and see equilibrium. I was astonished when with Hans Westman we did these simulations and found such a good relaxation just for a particle in a two-dimensional box. You can quantify the relaxation with the coarse-grained H function, which is minus the relative entropy of the density. With here, these overbars are coarse graining with respect to small coarse graining cells. There is a coarse graining H theorem, which is sort of broadly similar to the Gibbs coarse graining H theorem, assuming no initial fine-grained structure. This H function numerically is found to decay approximately exponentially with time. So in that example of the two-dimensional box I was showing you, here's a plot of log H versus T. You see there's approximate exponential decay. Similar simulations have been done for various systems, including the two-dimensional oscillator. So in this example, time is going downward. This is a bit weird, this pointer. Hang on. Sorry, hang on. What have I done? Okay. Where's the pointer? Ah, here it is. So time is going downwards. We have a 2D oscillator. Now there are 25, the first 25 energy states are superposed. And this is the initial psi squared. Okay, as it evolves in time, sorry, the units on the axis change a bit. That's why the height changes. But anyway, this is just psi squared evolving in time. The initial density we took to be a Gaussian. And this is how the density evolves with time, again, with some coarse graining. And again, note the remarkable relaxation towards equilibrium. Again, H decays approximately exponentially with time. Here's a plot of H versus T. Studies have been done of the relaxation time that depends on the number of modes. It depends on the coarse graining length. There are various papers about this. I won't go into too many details. Let me move on and just draw a moral of the story. We started 5 or 10 minutes late, right? So, yeah, all right, okay, all right. So, quantum relaxation. So I claim that in pilot wave theory, you can explain the Born rule. It's not a law of physics. It's an equilibrium distribution. Just like in classical statistical physics, Maxwell's distribution of molecular speeds. It's not a fundamental law. It's a property of the thermal equilibrium state, which you can explain by a dynamical process of relaxation. And in principle, I can have a gas that is not in thermal equilibrium, where the distribution of speeds is not given by the Maxwell distribution. I claim that the similar is true here. And the Born rule, we see the Born rule in the lab and everywhere we look, not because it's a law of nature, but because we're stuck in this equilibrium state. Now, if you think about this, when would relaxation have occurred? If I go in the lab and I take a hydrogen atom, it's not been sitting in a vacuum for 13 billion years waiting for you to go and look at it. It's interactive with other things. It has a long history. And those of us who know our astrophysics know that all the matter we see around us has a long, complicated astrophysical history going back to the Big Bang. And if you think this through, if something like this relaxation process occurred, it must have happened at the beginning of the universe, or very close to, in the violence of the Big Bang. So presumably, something like this happened in the early universe. So the claim is that we are stuck in this region because at some point in the remote past, a dynamical process of relaxation took us here, and we're stuck in here. And quantum theory is the effective description of a special state of statistical equilibrium. Now, people who work on foundations of quantum mechanics tend not to like this idea. They think quantum mechanics is fundamental, it's confirmed all these experiments. How can it just be an effective theory of a special state? But I think people who are in particle physics, we already know that the physics we see is the physics of a special state. We live in a spontaneously broken low energy vacuum minimum. The W boson appears to be massive. We know that fundamentally the fields are not really, they're really massless. They've just got an effective mass because they interact with the Higgs field. We're used to the idea that the physics we see is not really fundamental. It's the physics of a special state. And which is why often when I talk to people in particle physics about this, okay, it sounds reasonable. Unfortunately, in the field of quantum foundations, people tend not to like this. But anyway, when did quantum relaxation happen? As I said, presumably a long time ago, soon after the Big Bang. If so, we can expect that quantum theory will break down close to the Big Bang. So we should be looking closely at the early universe for possible evidence of deviations from the Born rule and some evidence that this relaxation occurred. So I'm going to give you a little sketch. I've done quite a lot of work on that over the years. I'm not going to go into much detail, so I'm going to whiz through a bit. Those who are familiar with these things will see what I'm talking about. Those who are interested can read the papers. Basically, according to inflationary cosmology, which of course may or may not be correct, but if inflation is true, then the temperature anisotropies we see in the CMB are ultimately generated by the Born rule. The early inflationary vacuum, approximately Bunch-Davies vacuum, you have a probability distribution for the inflaton perturbations. They're calculated using the Born rule. Okay, so the statistics of what we see on the sky is a reflection of the Born rule according to this theory at a very early time. Could there be signatures of quantum relaxation? Over a series of papers here, some with Samuel Collin, this last paper is a data analysis with Sandro Vitenti, who was here, and then Patrick Peter. Let me whiz through a few key points here, because there's a lot of stuff I could discuss, but let me go through some highlights. Remember, I've talked about quantum relaxation for a particle in a box, for a two-dimensional oscillator, what happens on expanding space? So I can look at the quantum relaxation for a field, say a scalar field in space. To simplify things, let's look at one mode of the scalar field. So we look at the field in Fourier space. We've got a Fourier component of the scalar field. It has a real and imaginary part. So we've got a two-dimensional system. Mathematically, it's like an oscillator. On expanding space, it's like an oscillator with a time-dependent mass. People in cosmology all know this. And we've done simulations of quantum relaxation for a single mode of a scalar field on an expanding space, which we took to be radiation dominated. So scale factor going as t to the half. All right. This was done with a couple of papers with Samuel Collin. That relaxation, we find that at long wavelengths, in particular wavelengths larger than the Hubble radius, relaxation is suppressed or retarded. So let me show you some simulations. So on the right-hand side, let's focus first on the right-hand side. There's no expanding space here. This is just a scalar field on a flat fixed background. And here I have, again, time is going downwards. So here you have, this is a two-dimensional configuration space, which, as I said, is the real and imaginary part of the Fourier mode. So it's a 2D, the mathematics is actually the same as the 2D oscillator in this case. Okay, and again, I have a superposition of 25 energy states. So this is psi squared initially, and this is the time evolution of psi squared. We start out with an actual density, which is a Gaussian. Okay, so the density is not equal to psi squared. It's a Gaussian. We evolve it forward in time, and look what happens. Again, you get this wonderful, remarkable. Every time I look at this, I'm still surprised at how good it is. But I promise you, we haven't fudged anything. Different people have independently written codes. We've done all possible cross checks we could think of. Okay, this is what happens. You get this relaxation. Now we do the similar system, the same thing, but on expanding space, and with the wavelength of the mode, if I remember rightly, I think was 10 times the Hubble radius. I don't quite remember. Anyway, it's in the paper. Here is again, the initial psi squared evolving in time. And here's the initial density. Here's the initial density. There's a Gaussian. We follow its time evolution. As you see, it evolves towards equilibrium. But it doesn't quite reach there. It's kind of squeezed. It's squeezed. It's sort of getting there, but it's squeezed. Sorry, this is maybe not so clear, but psi squared, as you see, is much more spread out than here. So it's as if it's trying to relax, but it doesn't quite get there. So long wavelengths mode, the relaxation is retarded. And there's a whole explanation for this in terms of a retarded time. We have an exact solution. Anyway, I won't go into that, but if people are interested, look at the paper. Here is a plot of h, log h against t, with no spatial expansion. You get this approximate exponential decay. With spatial expansion, you get this retardation. So there's a suppression of quantum noise at large scales on expanding space. Bear in mind that at short wavelengths, much smaller than the Hubble radius, the mathematics is just like this with no expanding space. So you get this efficient relaxation at very short wavelengths, at very long wavelengths, you get a retardation. And of course, for wavelengths in between, you'll get a bit of retardation. Anyway, so here's an idea, is something we've studied is the following scenario, is and imagine that before inflation, there was in some models, there's a pre-inflationary era, which might be radiation dominated. And let's imagine that the beginning of that era, you have non-equilibrium, and you study relaxation that I've just been showing you during this era, and then there's a transition to inflation. You would expect that at the beginning of inflation, at long wavelengths, there will be a power deficit. Remember that density was squeezed with respect to the Born rule. And of course, in inflation, you've got this field perturbation that generates an early curvature perturbation, which is what maps into the temperature anisotropy that we see in the sky. So now, if I write the width, here is the width of this Fourier mode. If I say it's equal to the quantum width times some deficit function, Okay, there's a power deficit at the end of pre-inflation. What we've done, the simulation I showed you where you find that it's squeezed, we repeated it for many different wavelengths. And you find that this squeezing factor, so at short wavelengths, you know, it approaches 1, there's no squeezing. At long wavelengths, you get the power deficit. These are simulations for different numbers of modes. There's a lot of detail that I'm just skipping over here. But if we, to a first approximation, ignore the oscillations, numerically, we find a fit to an inverse tangent function with 3 parameters. Okay, so there's a sort of, and there are some simplifying assumptions here that I don't have time to go into, but basically we have as a first approximate simplified model, we have something like a prediction that we could look for in the data. Now, of course, the Planck results, they reported a power deficit at large scales, which has been controversial. Could it have something to do with this effect here, this squeezing, this retardation, this suppression of the Born rule at long wavelengths? Maybe, maybe not. So a topic for another talk is I did a very extensive data analysis with Sandro Vitenti and Patrick Peter, she published a few years ago. There's some intriguing stuff. If Nelson invites me back sometime, I can give you a talk just about that. There's some intriguing stuff, but some hints, but nothing clear or definite. There's another topic for another talk, which is the idea that there could be relic particles that decoupled at very early times that could still exist today, perhaps the components of dark matter. There are theories of dark matter, for instance, made of gravitinos, for example, that's supposed to have decoupled very early on. Conceivably, such particles, if you follow this kind of thinking, maybe they didn't have time to reach equilibrium before they decoupled, and they could still be out of equilibrium now. I've got some papers on that. Let me move on. Remember what I showed you at the very beginning. What I wanted to convince you of is this idea that when you go home this evening and you're thinking, that Valentini, what was all that about? This is the only thing really I'm hoping you'll remember, is that quantum theory is a special case of a much wider physics. We're stuck in this region. We have locality. I'll talk about locality in a moment. We have quantum noise, the Born rule. But these are not laws of physics. There's a wider physics out here, and we're stuck in here because of some past process of relaxation. Now, if you think about this, it's a little bit like something that people worried about in the late 19th century, the classical thermodynamic heat death. Okay, in the late 19th century, Clausius, Boltzmann, various people realized that, well, eventually the stars will have to burn out. The universe is running down, entropy is increasing, temperatures are evening out, heat flows from hot to cold, and not the other way. Eventually, in the distant future, we will reach a state of uniform thermal equilibrium where everything in the universe is at the same temperature. Now, the claim here is if you take pilot wave theory seriously, at least as I understand it, a microscopic analog of the classical heat death has already happened a long time ago. We're stuck in this state of not of universal thermal noise, but of universal quantum noise, given by the Born rule, which is not a law of nature, it's a state of equilibrium. And there are, now, you know, if I can just let this sink in for a minute, I mean, it's saying that with the physics that we're looking at is a very restricted special state. Okay, imagine we lived in a world where everything was at the same temperature. You wouldn't be able to convert heat into work. You need differences of temperature to convert heat into work, okay? We live in a world where everything has this same quantum noise. You would expect there to be some peculiar restrictions in such a state. And indeed, the fact that we're stuck in this state, I think explains why we cannot use quantum non-locality for signaling. So in the classical heat death, you cannot convert heat into useful work. In this quantum death, you cannot convert entanglement into useful superluminal signals. Now, by now, I think there is a a consensus would be wrong, but there's a general realization that when you have entangled systems, no matter how far apart they may be, there's a reasonable case for believing that some kind of non-locality is going on. There's something non-local. There's controversy about exactly what it is, and so on and so on. But if you think about this, if there really is something, you know, in the EPI, I've got two entangled spins, for example, in the singlet state, and it appears that in order to explain the correlations, there has to be something non-local going on. If that's true, if there is quantum non-locality, it raises a question. Why can't we use it for signaling? Okay? There are these strange correlations seem to be non-local, but if I look at the marginal distribution here, I can't see any non-local influence. If over there somebody does something, they change the setting on the equipment, I don't notice anything here. There's no actual visible non-local signal. Why? If there's non-locality, why can't I actually see it? Why do I have to just deduce it's there indirectly? Now, pilot wave theory is highly non-local. If you look at a system of two particles in ordinary three space, the configuration space, the trajectory is guided by a wave in configuration space. And it's non-local in the sense that if I move one particle, the velocity of the other particle whoops, I haven't got the hang of this. The velocity of the other particle changes, okay? So have your entangled systems, the velocity of this particle depends instantaneously on where the other particle is. And in fact, there's more to it than that. If I change the local Hamiltonian here, switch on a local electric field or something, the velocity of this particle instantly begins to change in response to it. It's a highly non-local theory. So you may ask, well, why can't I send signals in this theory? And the answer is, in principle, you can send signals instantaneously if you're out of equilibrium. Here is an example of, I have particle in the box here, a particle in the box here, and they're entangled. Okay, they're in an entangled state. So if I change the Hamiltonian here, for instance, I move the walls of the box, the velocity of this particle responds instantaneously. Now, if I have an ensemble of such entangled pairs, if I change the local Hamiltonian here, all the particles in here start to move in response, okay? Now I can calculate the time evolution of these trajectories, and I can calculate the time evolution of the marginal distribution. And what you find is that that if the joint probability density for the ensemble is equal to psi squared, then the marginal is local. So you imagine some particles, maybe when you change the Hamiltonian here, this particle instantaneously begins to move this way, but this other particle instantaneously begins to move the other way. And overall, for an equilibrium system, the marginal distribution does not change. However, and you can calculate this explicitly, if you're out of equilibrium for a joint distribution that is not psi squared, the marginal distribution changes instantaneously in response to what you do over there. So what this theory is telling you, again, if you take pilot wave theory seriously, it is telling you that the equilibrium distribution is very finely tuned, okay? It's a fundamentally non-local theory. If I change the Hamiltonian here, there's an instantaneous response here. However, if I average over a Born rule ensemble, the effect cancels out, it averages to zero. If I'm out of equilibrium, it's non-zero. So if you have non-equilibrium ensembles, you can send non-local signals and define an absolute time. Remember at the beginning, I told you for the general system, I was assuming that I had a globally hyperbolic space-time, space-like hypersurfaces, configuration of fields on those hypersurfaces. In this theory, you have to assume that one of those foliations is the true foliation, that the non-locality will act along particular hypersurfaces, non-locally, instantaneously across certain hypersurfaces and not others. All right, so how you see now what I mean when I say that the physics outside of here is non-local. You can send instantaneous signals. Our inability to send instantaneous signals is a peculiarity of equilibrium. Just as if I was in a global heat death, I would not be able to convert heat into work. That's not a law of physics, it's a peculiarity of that state. Okay. All right. Maybe another 20 minutes? No, because we started a bit late. It's quarter to 5 by my clock. So anyway, okay. All right, okay. So here's a question for you. You may say, well, it's all very well, but then it's just a speculation. If we're stuck in this state and that's all we ever see, who will ever know the difference? I may as well just call the Born rule a law of physics, and you know, no, it won't make any difference. So, well, here's a question: are we trapped forever in a state of quantum death? Okay. As I said, there's this parallel with the classical thermodynamic heat death. Once it happens, is there a way to escape? So you might wonder, can we create non-equilibrium? So you might think that, well, if I have some particles in the lab that obey the Born rule, maybe if I do something with them, some rapid process, if maybe high energy particle collisions, maybe I can create non-equilibrium. It seems not. If you look at a theory where I have quantum systems on a classical space-time background, then it seems that this distribution is preserved in time by the dynamics, and once you're there, there's no way out of it. However, things are different when you involve gravity. Now, I gave a talk on this at the conference last week, but I'd just like to briefly say there were 3 main points. One was the claim that actually things are quite different. Everything I've been talking about, I think, is valid when you have a classical curved space-time background. Okay, but if the actual gravitational field or the space-time itself is quantum, then I think things are different. Now, in quantum gravity, my proposal actually is that there is no Born rule in quantum gravity, essentially because solutions of the Wheeler-DeWitt equation are non-normalizable. So necessarily a normalizable probability will always be different from psi squared. And this idea of quantum equilibrium, I think, is just not valid in the deep quantum gravity regime. And the Born rule can emerge when you have a semi-classical approximation. So you have, you know, from the Wheeler-DeWitt equation, you can derive an approximation, have an approximately classical space-time background with quantum fields on it that obey an effective time-dependent Schrödinger equation with normalizable wave functions. In such a situation, you can get the kind of quantum relaxation that I talked about. And still, so you still get the Born rule. Some say there's no Born rule fundamentally, but you can still explain why we see the Born rule in this approximate regime. There are also an interesting thing that tiny quantum gravitational corrections to the Schrödinger equation seem to make the Born rule unstable. It's possible for non-equilibrium to be created. Now, this just briefly, let me just focus on this last point. This goes back to work by Kiefer and Singh and also more recent work, where in a higher order semi-classical expansion of the Wheeler-DeWitt equation, they find small non-Hermitian terms. So these are quantum gravitational corrections to the Schrödinger equation for, say, a field on a background space-time. There are very small non-Hermitian terms. Now, when I say small, I mean very small because there's a Planck mass involved. So these are extremely tiny. And of course, they're inconsistent with standard quantum mechanics. But in pilot wave theory, it turns out that these terms just generate a small instability of the Born rule. You can deal with them consistently. And one particularly interesting scenario, I mean, there's a paper by Kiefer, Muller, and Singh where they talk about if I have a scalar field in the space-time of an evaporating black hole, there is a small non-Hermitian correction coming from quantum gravity that looks like this. That's significant only when the mass of the hole approaches the Planck mass. Now, if you treat this in pilot wave theory, it turns out that the deviations from the Born rule are generated on this time scale. So you would expect that in the very final burst of Hawking radiation, the last little bit of the hole as it evaporates, would break the Born rule. Now, this has only been treated with some rough estimates, I should add. Okay, these are just simple estimates of timescales, but it does look as if, in principle, you could have something like this, where you have a primordial black hole that formed in the very early universe and is now exploding, and you might detect the gamma rays, and at some level of accuracy, there could be some small deviation from the Born rule for some of the frequencies. Unfortunately, it would only be the very final burst, so whether you'd really be able to see this in practice, I don't know. It turns out that a satellite being launched next year has an interferometer on board to test the Born rule in space, so this kind of experiment is not entirely fanciful. Okay, a change of topic. I've talked a lot about trying to convince you that we're stuck in this certain equilibrium state, that the Born rule is not fundamental. It arose by a process of dynamical relaxation. I've talked about how this could have happened in the early universe and how there could be some signatures in the CMB of this happening. I've talked a little bit about how exotic quantum gravitational effects could perhaps give us a way of escaping from this state and actually seeing violations of the Born rule. And I've tried to convince you that the physics that we see is only the physics of a special state. So now there's a question, well, this broader physics, what would it look like? You've told us that the Born rule would be violated. If we had particles that violated the Born rule, we did a two-slit experiment, you'd see a blurring or a change in the interference pattern. Fair enough. You've told us that there would be superluminal signals for entangled systems. What else? What would this physics look like? So I'm going to talk a little bit, give you a flavor of some of this new physics. New physics beyond quantum mechanics. What would it be like? All right. So here's one thing, is that you could perform what I call sub-quantum measurements. So let's imagine first, just talk a little bit about how you could harness quantum non-equilibrium. Imagine these are some particles left over from the early universe, for example, and we think they might be out of equilibrium. They didn't quite relax and so on. Here I've given the example of hydrogen atoms in a ground state, just for simplicity, but anyway. Let's imagine, in order to how do you deal with non-equilibrium operationally? So here's one thing. Here you've got these atoms, which you assume they're independent, they're not entangled, and you suspect they're out of equilibrium. What do? Let's pick a random sample, and we measure their electron positions. Okay? And just by standard techniques, we can deduce the most likely parent distribution. So we've picked a random sample, we've measured their positions, we've deduced the most likely parent distribution. Now, the rest of the atoms that we haven't touched, we haven't measured, we haven't disturbed them, we know their parent distribution. And if it is non-equilibrium, then we can use the rest of the atoms to do things. So what could we do? So for example, imagine here there's a particle in one dimension. I want to measure its position. We know how to do that in quantum mechanics. You couple it to a pointer with this von Neumann interaction Hamiltonian. A is a coupling constant. I've got a position operator. This is the momentum conjugate to the pointer. This is a standard quantum measurement. However, if I do that measurement, so I measure the position of the particle from the value of the pointer moves depending on where the particle is. It tells me the position of the particle. When you do that, the wave function of the particle collapses. I haven't really discussed how this happens in Broglie-Bohm, but basically the total wave function separates into branches depending on where the pointer moves to, and you get an effective collapse of the wave function. Can we avoid that? We can if we're out of equilibrium. So what we're going to do, we're going to say the particle is an ordinary equilibrium system, but the pointer is a non-equilibrium pointer. So it has a known wave function and it has a known non-equilibrium distribution. So now we might be thinking of ensembles. You know, we're doing this experiment and we have an ensemble of copies of this experiment. We're going to assume that the pointer has a distribution that is not equal to its wave function squared. Now, for this simple Hamiltonian, you can solve this system exactly. The de Broglie equations of motion are very simple. You can solve for the trajectories. I won't go into the details because I can show you everything with a picture, but let me just look at this example. Imagine I have an initial wave function that's a superposition of two positions. So the particle is either here or it's here. Okay, and I want to measure, it's a superposition of x is L or x is minus L. And I want to measure its position without disturbing the wave function. So I couple to the pointer, and the Schrödinger equation implies this time evolution. So the pointer moves one way or the other way, depending on where the particle is. We can calculate the time evolution of any initial joint distribution, even for a non-equilibrium distribution. Never mind the equation, it's an exactly solvable system. I can show you what it looks like with a picture. Let's imagine, first look at the case of an equilibrium pointer. So it's standard quantum mechanics. This is a plot here. So I'm in configuration space, got the pointer y, the particle position x. This is the region, the shaded region is where psi squared is non-zero. So the particle is concentrated at minus L or plus L, and the pointer, this is the width of the wave function of the pointer. Okay, so this is a plot of the initial psi squared. As you switch on the interaction, it evolves with time like this. Okay, there is a separation in y space. Now, if I look at the pointer and I find the pointer has some positive value, say in here, well, I then know that x must have been plus L. Okay, because it's the only possible. If instead I'm here, if I look at the pointer here, and I find this positive value of y, I don't know if I'm here or I'm here. In order to have an unambiguous measurement, I have to wait for there to be a separation in y space, okay? So it takes a certain time. Now, let's look at what happens if instead I have a narrow non-equilibrium pointer where the width of the distribution is less than the width of the wave function. The separation needs a shorter time. So here I've got the shaded region is the region where the probability is non-zero, okay? The white region here, this is the width of psi squared. This is the width of the actual distribution. It's smaller, the width. So I've got this pointer wave function, but the actual probability distribution for the pointer is a narrow thing inside, okay? You see here that you get a separation at this time. If I find that the pointer is in here, I already know that x was plus L, okay, because there's no probability in here for the pointer. If I was in equilibrium, I would not have an unambiguous measurement yet. If I found y in here, I wouldn't know, well, am I in here or am I in here? I wouldn't know if x is plus L or minus L. So the point is, for a narrow non-equilibrium pointer distribution, you can get an unambiguous measurement in a shorter time. Now, if you imagine the limit where the actual density of the pointer is arbitrarily narrow, I can get an unambiguous measurement of the position of the particle for arbitrarily short times, where the total wave function has hardly changed. So in other words, I could measure the position of the particle without changing the wave function to arbitrary accuracy. So in the limit of zero dispersion, I recover an analog of the classical ideal non-disturbing measurement. And if I repeated this, over many times, I could track a trajectory, again, assuming arbitrarily narrow non-equilibrium distributions. In principle, I could track trajectories without disturbing the wave function. Okay, so what could we do with it? Just another few minutes and I'll be done. So a few things that this would imply. So first of all, we could distinguish non-orthogonal quantum states. It's a basic theorem of quantum mechanics. So you give me one copy of a quantum state and another copy of a quantum state. If they're not orthogonal, I have no way of telling which is which. I would need to do experiments over ensembles. Okay. Now, in pilot wave theory, different states, even if they're non-orthogonal, in general, they generate different velocity fields. So the trajectories, these two wave functions will have different trajectories. If I can track the trajectories without disturbing the wave function, I could distinguish non-orthogonal states without disturbing them. So we could use that, for example, for eavesdropping on quantum key distribution. Those who are familiar with these things, Alice and Bob want to share a secret key that they're going to use for encryption and cryptography. And they do this by, there's one well-known protocol that relies on Alice's sending a random sequence of two states that are non-orthogonal. And there's a protocol that I won't go into, but basically this is supposed to be that you cannot eavesdrop, because if Eve is trying to monitor which states are being sent, she would disturb the states in a way that is noticeable. Okay, but if Eve possessed non-equilibrium particles, she could distinguish the states without disturbing them and so read the key. So basically you could break quantum cryptography, so the quantum internet could be hacked. Similar, another protocol, this is quite an interesting protocol by Arthur Eckert in 1991, where basically I've got a pair of entangled particles, and you know, if I measure spins along the same axis, I always get opposite results. And there's a way of using this to share a key between Alice and Bob, which you know, and the statement is, well, an eavesdropper cannot predict what the outcomes are going to be. It cannot predict what the shared key is going to be because there's nothing there. The reality comes into existence only when measurements are made. But if Eve here, the eavesdropper, possesses subquantum non-equilibrium matter, they could in principle monitor the particles and predict the keys that are being generated at these different wings, and so eavesdrop again on the system. Finally, one last thing, just another couple of slides and I'll be done. 5 minutes? Okay, no problem. So subquantum computation. Possibly there could be a more powerful form of computation in which you use this ability to distinguish non-orthogonal states, something that was actually looked at by Abrams and Lloyd back in the late 90s in the context of nonlinear quantum mechanics, which can allow non-orthogonal states to evolve into orthogonal states. They looked at an algorithm where if you use nonlinearities to distinguish non-orthogonal states, you could get a more powerful form of computation. So I looked in a paper of 2002, I looked at a similar thing, but using the fact that a subquantum measurement could distinguish the non-orthogonal states. Now, the thing is about this, I mean, at the moment, it's not known what the power of this could be. And basically because, I mean, I made a bit of a premature claim in this paper, but basically looking at it more carefully, if you want to define a model of computational complexity and the power of these kinds of algorithms, you need to quantify the resources, and you need to know how the resources scale with the size of the task. If the resources scale exponentially, then that's no good. So a study needs to be made basically in order to, if I have non-orthogonal states that are very close, they're almost the same, they're just slightly different. Okay, I'm going to need a very narrow non-equilibrium distribution in order to distinguish them. Okay, and as the difference between the states gets very small, this distribution will get narrower and narrower. And the question is, how does the resource scale with the size of the task? It's not been studied. So actually don't know what the power of this, but certainly novel kinds of computation can be done by distinguishing non-orthogonal states. So finally, let me take home message. The quantum death trap. This Valentini, what was all that about? What was he talking about? This is what I was talking about, that we live in a state of quantum death. What we see is restricted by the uncertainty principle. There's this quantum noise everywhere that prevents us from controlling non-locality and using it for signaling. All these constraints, you can't distinguish non-orthogonal states. None of this is as a law of physics. It's a peculiarity of this state that we're statistical state of equilibrium that we're stuck in. Outside here, there's a wider physics of superluminal signaling, of all kinds of new technology. And if that sounds, if you want to, as a parallel that I've mentioned, is imagine some hypothetical beings that lived in a state of global thermal equilibrium. They would think it's a law of physics that all systems have a universal thermal noise at temperature T, law of physics. It's impossible to convert heat into work, law of physics. Of course, beings couldn't really exist in such a world, so this is just sort of fanciful. But imagine if beings exist in such a world, they would believe that Maxwell's distribution of molecular speeds is a fundamental law. The only way to convince them this is not true would be to show them some sort of way out. How can you get out of this state? And, you know, this state where you can have steam engines, sunshine, life, all these things. I've tried to convince you that we are in a comparable state, that we are stuck in here and there's something much bigger and better and more interesting beyond, if only we can find our way out of it. Now, I don't know if I've managed to convince any of you, but if anyone wants to know more about this, I have 2 books coming out next year. One is a technical book aimed at advanced undergrads, beginning graduate students, and the other is a book for the general public, Beyond the Quantum. So if you want your grandmother or grandson or friend, or, you know, if you want to give them the news that there's this much bigger physics beyond what we currently know, beyond the quantum, then this is the book. There we are. Thank you so much. Thank you.
Thank you, Antony, for talk. Okay.
Hi. I would like to understand, how can you talk in causality, locality, in a world without Pauli-Jordan function?
Sorry, how can you
talk in causality and locality and so on in a world without the Pauli-Jordan function?
The Pauli-Jordan function?
Yeah, exactly. Pauli-Jordan.
Sorry, what is the Pauli-Jordan function?
It's the commutator in between 2 fields that gives causality, locality. Right?
Ah, right. Oh, I see. I see. Okay. All right. So, quantum field theory. Field operators commute, space-like separations, and so on and so forth. None of that is changed. So if you look at the pilot wave theory of fields, which is usually done in the functional Schrödinger picture. So you take your standard quantum field theory, you write it in the functional Schrödinger picture in a given frame, and it's exactly the same. That is the Schrödinger equation for the wave functional. There's no difference. What is added is an equation of motion for the time evolution of the field. Basically, the time derivative of the field is given by the functional derivative of the phase. It's the same kind of construction. Now, if you have an equilibrium distribution, then you get exactly the same predictions as standard quantum theory. It's just the probability distributions of the fields are given by mod psi squared. If you want, you can rewrite in the Heisenberg picture. You've got all the same stuff. If you're out of equilibrium, then you would notice that the time for an entangled state, if the field elements here entangled with field elements over there have an entangled wave functional, then the motion of the field here will depend instantaneously if you change the local Hamiltonian here. And over an ensemble, the marginal distribution would respond instantaneously. Which is fine as long as you assume there is a preferred frame. Okay, this is all done in a preferred frame. Now, the mathematics of the Schrödinger wave functional, or if you like, rewriting it in the Heisenberg picture, is completely unchanged. So all of the usual mathematical machinery is there in the Schrödinger, is not changed. You're just adding something. So, I mean, what I suppose I could say is if you look at, yeah, I mean, I think that's it. Okay.
More questions?
If your kind of H theorem is okay, then there is no way to escape from Born assumption. If you can escape, then that theorem is not a theorem, is not true. So do you see any way to
Right.
make these
Okay.
two statements
Right, okay.
compatible?
Okay, so so sorry, yeah, I mean so fair enough. So what I talked, I mean, I talked a little bit how the picture is different if you go to quantum gravity. So if you're on a classical curved space-time, a classical background space-time, then it looks as if you get relaxation, and once you're there, you're stuck there, and there's no way to escape. If instead you're talking about a regime where quantum gravity is important, then, I mean, I was a bit quick because I gave a talk about this last week, but the picture changes quite drastically. First of all, in the deep quantum gravity regime, the wave functional is static and non-normalizable, okay? So I've argued that this means that there is no Born rule, fundamentally. Probabilities all cannot be equal to psi squared. And in fact, I have a paper coming out very soon with a former student of mine, Aditya, that Chico knows, where we've looked at this in a model of quantum cosmology. So it's a simplified model of quantum gravity, model of quantum cosmology, where the wave function is non-normalizable. And we've done simulations. So you can, let's say I've got the two-dimensional mini superspace model of quantum cosmology. The wave function is static and non-normalizable, okay? Let's start off with a distribution, some localized distribution, a Gaussian, like what I've done there, and let it evolve in time numerically. Does it relax? Does it perhaps relax locally in some region? The answer is it doesn't. The evidence that we've gathered, the examples we've looked at, you don't get the kind of relaxation that you see for normalizable time-dependent wave functions does not occur in the deep quantum gravity regime. It occurs only when you're in a semi-classical regime where you have an effective time-dependent wave function on a classical space-time background. Then you get relaxation. But then there is this further thing that, according to Kiefer and collaborators, if you then calculate corrections to the effective Schrödinger equation in the semi-classical regime, there are small non-Hermitian terms, which most people try to either discard or eliminate somehow because they don't make sense in quantum mechanics. If those terms are actually there, these are very small quantum gravitational effects, which there's no hope of seeing in the lab. I mean, these are extremely small. But in principle, if they are there, if they're not artifacts, then they can make an initial equilibrium state evolve away from equilibrium. But the effects are extremely small. And in fact, the only place I've managed to see where it looked as if there may be some hope of seeing this would be in a final stage of a black hole evaporation. Does that answer your question, kind of? So, I mean, basically, all this story about the H-shear and relaxation and being stuck in equilibrium, it applies, as far as I can see, when you ignore quantum gravity. But when quantum gravity is involved, it can change the situation, possibly.
There is no Born rule?
Yeah.
Yeah, that.
So I think that the H-shear doesn't work.
But in our experiment, like a
No, we're trying, but no.
When you mention CMB radiation,
Yes.
I don't know whether I got the point, because I know how to use CMB to measure Gaussianity, to detect topology of the universe, but I didn't get the point. Are you expecting to have a modification CMB power spectrum? Is that the point?
Yes, sorry. Yes.
Where for each scale?
Sorry?
For each scale.
So for large scales. Large scale. So if you do simulations of relaxation in what we assume could be a pre-inflationary era, then you get the usual relaxation at short wavelengths, but at long wavelengths it's suppressed. So you would expect that as you enter the inflationary era, the usual power spectrum would the small values of wave number, that it would dip. And we actually have a sort of approximate prediction for that. So yes, it's a large-scale power deficit is what we expect. And according to the the observations, there is some, I mean, the statistical significance is small, but there are reported anomalies. Power deficit has been reported at large scale. Some people think it's just noise. It's just a statistical fluctuation. It's not actually any actual new physics. But there's also statistical anisotropy reported in the same region. And, I mean, I've been very quick here. There's a long story I could tell also about statistical anisotropy. In this theory, you would expect statistical anisotropy. Also, for those who know about these things, in this theory, you would also expect a breaking of the scalar tensor consistency condition, because the scalar perturbations and the tensor perturbation, they're different degrees of freedom. If they're out of equilibrium, there's no reason why they have to be related. And, there are issues about polarization. There are some anomalies. If you look at the CMB sky in polarization, you look at it in terms of temperature, they don't seem to quite match. And there are various things like that are similar to what I would expect. But of course, how to make it quantitative and get a fit, we've got a long way to go. We have a sort of approximate prediction for the power deficit large scales. We've done some fitting, but that's the kind of thing I'm looking at.
May I ask a second question? Apart from CMB, do you have, say, a lab way of, say, detect or falsify or model at some, say, energy scale or something like that?
Right. So, there is a Broglie-Bohm theory of, high energy physics, quantum field theory, and so on. And again, if you have, the functional Schrödinger picture on a fixed space-time background, it looks as if when you're in equilibrium, you're stuck there. It's only if quantum gravitational effects could come into play that maybe you would see something. Unless there's something unexpected. I mean, is there something we don't know, that maybe at certain energies, there's some modification of this picture. I'm afraid the one possibility, which again, as I said, would be also a subject for another talk, would be the idea that there could be relic non-equilibrium particles left over from the very early universe. There are quite prominent theories of dark matter, which suggest that the dark matter is made of exotic particles left over from the very early universe, which would have expected to have decoupled extremely early. Possibly they could be out of equilibrium. And there are experiments going on where people are looking, for example, for dark matter and say gravitino annihilations, producing gamma rays and looking for signatures of annihilating dark matter. If they violated the Born rule, we would expect the photons that they produce to violate the Born rule. So, the closest I can get to you as a lab experiment would be that if we find annihilating dark matter, I'd be interested to test the photons to see if they obey the Born rule. But it's not easy. No.
Can you define again pre-quantum? You said pre-quantum. Before quantum, what it was pre.
So subquantum.
Subquantum, pre-sub, yeah. Can you define?
So what I mean by subquantum is just something that is certain details that quantum mechanics does not talk about. So it's something, if you like, beneath quantum mechanics. So quantum mechanics just talks about probabilities for ensembles. It doesn't give you a picture of exactly what is happening for an individual system. So these trajectories are something that quantum mechanics is simply silent about. It doesn't talk about them. So when I say subquantum, I just mean something. Yes. Yes, no, exactly. No, exactly. In order to see these to see the details of these trajectories, you would have to violate the uncertainty principle. And I showed you that if you had equipment that it was in a state of non-equilibrium, you could use it to monitor trajectories without collapsing the wave function and actually see what is going on. So if we find non-equilibrium matter left over from the early universe, or if we find non-equilibrium particles radiated by an evaporating black hole, these are the only. That's all right. We all have. Sorry?
I remember measurements is about equilibrium, no? When we measure.
When we measure, it's about equilibrium, no? It's already when you
sorry.
do the measurement, right?
Standard quantum measurements. It's all from this point of
I mean,
view.
how we do
equilibrium
right
systems.
now, right? For instance, in every lab when we do quantum,
It's all
computers and all of this.
It's all in quantum equilibrium. already.
Yeah, that's what I'm asking. So I was taught in Russia that measurement is about equilibrium, like statistical sort of equilibrium, right? And you talking about non-equilibrium state.
Yes.
How you gonna even deviations from the, and what's the scale of deviation? Like Planck scale?
Probably. It might be.
But
Sorry. Maybe we can.
He's saying
talk-
that everything
maybe we can
is
talk
quantum equilibrium, so everything is in accordance with the Born rule. But there are some, perhaps there are some special things in the universe. Yeah, yes, the speculation. Yeah.
Listen, if I knew it was true, it wouldn't be research.
So,
All right. So
since Valentini seems a little hesitant to comment, I was gonna ask it about you, to you. Nowadays we have a quantum field theory treatment of general relativity that shows that we have some kind of access to the quantum theory of gravity by low energy perturbations calculations. And when you consider only conventional treatments, you get incredibly small corrections in the low energy regime. So obviously in labs, you won't find any signature of that. On the other hand, nowadays we have a bunch of experiments and a bunch of new theories that propose some explanation of the collapse postulate by quantum gravitational justifications. So in your theory, I know that you have these Hermitian corrections, but in principle, if we were to give a full quantum field theoretical treatment and calculate these perturbative corrections to some laboratory systems that are currently being tested for quantum gravitational low energy signals that usually appear as deviations of standard quantum mechanical measurements. Shouldn't we be looking for this kind of low energy perturbative corrections in some of these macroscopic superposition, gravitational mediated entanglement, this kind of curved space quantum mechanics experiments?
So it's a good idea. It's a good idea, Chico. I think it would be a good thing to look at. Would there be a particular reason to expect non-equilibrium to be generated? Possibly. People have talked about, there is an ongoing controversy, as you know, about gravitational time dilation inducing an effective decoherence. If such effects are real, would they generate non-equilibrium? There's a whole lot of things one could explore there. So that would be something to look at, certainly.
Yeah.
Hi.
Felipe, hello.
Yeah. Okay, so I have two maybe fundamental or basic questions. So you presented the pilot wave theory as a non-relativistic particles come from the Schrödinger equations, all that, and show that the velocity is the gradient of the phase, basically, right? So that's a postulate, or you can read off from the Schrödinger equation. From your, it's
well.
How do you approach this? Because
okay, so I think about it as it's a natural velocity field that appears from the Schrödinger equation. But of course, you could always add a term to the current that is divergence free.
Yeah.
So you could have a different velocity field, but let's say it's the simplest velocity field. that is associated with the continuity equation that you get from the Schrödinger
And
equation.
what if you have a system that your Schrödinger equation gives you a velocity field that has nothing to do with gravity of s? Like
Yeah.
we know some kind of systems like
Oh,
this. They put
sorry,
interactions
no,
and
sorry, yeah, no, okay, sorry, no, sorry, you're asking, I thought you were asking about something else. No, I know exactly what you mean. Sorry. So well, actually, yes, look, if the velocity field that you get from the Schrödinger equation depends on the Hamiltonian.
yeah.
So for instance, for that simple measurement Hamiltonian I gave you,
Mhm.
the velocities don't even depend on the wave function, they're just simple trajectories. If the Hamiltonian is quadratic in the momentum, then you get this gradient of phase. If you have more general Hamiltonians, you can have different velocity fields. I have a paper with Ward-Struve where we derive a general expression for the velocity field for if you have a Hamiltonian that is given by a finite differential operator. So in other words, it's a sum of terms with arbitrary powers of p's and q's. We derive the general velocity field. And it depends on the velocity field depends on the Hamiltonian.
So you must read off from the Schrödinger equation.
Yes.
Okay.
Yes.
Okay.
Yes. Yes.
And the second question, it's a little bit more tricky. How should I understand the wave function? Like, what is the wave function like for many particles? Systems, like it lives in configuration space. It's a real thing. It's just information. How do I understand that?
Yeah.
Because
So
sorry, because the particle lives in space time, right? Every particle lives in space time. So how do I do this?
Yeah. Well, look, there are different opinions about this. So the way I look at it, I think if you take this theory seriously as it stands, then you have to think of the wave function as a real kind of object, even though it lives in configuration space. And it affects the motions of systems, it determines the motions of systems of things that we see. Now, some people like to suggest that, no, it can't be a real physical thing. You must think of it as just some kind of mathematical thing, or maybe a bit like a law, or a bit like a Hamiltonian, that do a Goldstein-Zangi proposes view. I tell you why I don't think that's right. And it's basically because the wave function, it's not just a fixed thing like the Hamiltonian of a system. It doesn't have a fixed law-like quality. It's something that it could be different. Even in the case of quantum gravity, where the wave function is static, you might think, okay, it's not changing, so it's a fixed thing. Maybe it's just some kind of mathematical law. It's not a real object. But there are infinitely many different solutions of the Wheeler-DeWitt equation. Okay, the wave function of our universe is a particular object. It could have been different. Now, some people argue that, well, there's only one universe and one wave function. So I can just think of it as a sort of given law-like thing, not as a physical object. But, there's only one space-time geometry for the universe. And yet we think of it as a physical thing that could have been different because there are many different solutions of the Einstein equations. So, it seems to me that the wave function, even of the wave function of the universe, has this sort of contingency. It's an object that it could have been different, it could have taken different forms, and it has a complex structure. Seems to me there's no getting away from thinking of it as a physical thing, a bit like the electromagnetic field, a bit like space-time geometry. It just lives in this configuration space. Could it be that maybe in some future theory it will turn out to be just some effective description? Maybe all this comes out of something deeper. And the wave function would emerge as just some effective thing. We don't know. But as the theory stands, that's the way I look at it.
Thanks, fair enough.
Hello. I want to know if if there's some hypothesis as to why quantum gravity would cause non-equilibrium. Like why does non-equilibrium arise out of quantum gravity?
So sorry, as I said, I went over that very briefly. So basically, it started in 1991. There's an interesting paper by Kiefer and Singh, where they start from the timeless Wheeler-DeWitt equation. And by a semi-classical approximation, they derive the effective Schrödinger equation for a scalar field on a background classical space-time, okay? And you get the usual Schrödinger equation, time-dependent, that you expect. They then calculated higher order corrections to this Schrödinger equation. And the corrections take the form of small corrections to the Hamiltonian that are suppressed by the Planck mass, are extremely small. And these corrections, some of them are Hermitian and some are non-Hermitian. Now, similar calculations have been done, and there's a series of papers going over 2 or 3 decades now with Kiefer and collaborators, also in quantum cosmological models, where you get the same thing, the quantum gravitational corrections. For instance, there's a paper maybe about 10 years ago, so several papers, looking at this in quantum cosmology. So quantum gravitational corrections to the Schrödinger equation and applying it to inflation, okay, and deriving small corrections to the power spectrum. There are small corrections to the Hamiltonian coming from quantum gravity that they calculate, and they say, what is the effect on the CMB? It's extremely small. But when you look at this, the corrections to the Hamiltonian, there are Hermitian and non-Hermitian terms. Now, what they do is the non-Hermitian terms, they just throw them away, because how do you deal with those in quantum mechanics? They violate unitarity. They've also done things like redefining the wave function in a way that eliminates these terms. Now, there's a question here. Are the non-Hermitian terms just artifacts of the approximation? Is it just incorrect? Or are they real physical effects? Now, in standard quantum mechanics, I think you're almost forced to take the view that, well, they must be just artifacts because they don't make any sense. So let's redefine things, let's just throw them away, let's do something to get rid of them. In pilot wave theory, it's quite straightforward, and sorry I didn't go into the details, but basically, the continuity equation for the density is unchanged. You've got the same velocity field and you can evolve the density. But the continuity equation for the psi squared is modified because of the non-Hermitian term, the Schrödinger equation. There's a source term. So basically, this theorem I showed you about if rho is psi squared initially, it remains psi squared, breaks down. You can have, if I start out with the Born rule, it can evolve to a non-Born rule state, but the effects are extremely small, and they're there if you take these non-Hermitian terms seriously. That's where it comes from.
I see. Thank you.
One last question. So I was wondering if I turn off or turn on some kind of interactions, so then I'm going to change the whole game. And then I could.
Sorry, if you turn on or turn off what?
Some kind of new interaction. Like I create some kind of interactions, like or I turn off electromagnets, for instance. Like I suddenly say that I'm going to shut down all kind of electromagnetic interactions. So in this scenario, I think that I could probably go out of equilibrium, right? Because I'm going to change completely how the systems is going to interact.
So what you would be doing, if I understand you would be saying that, for instance, in the Hamiltonian,
yeah,
the coupling constants could be switched off.
Yeah.
Okay.
On or off.
On or off. But the thing is, you see, changing the Hamiltonian, if I'm in a situation where I have a time-dependent Schrödinger equation on a fixed space-time background, even if the Hamiltonian is time-dependent, psi squared is still preserved by the dynamics. The velocity field would change. If you're changing the Hamiltonian, the velocity fields would change.
Yeah.
But the theorem would still be there. I don't think you would create.
But for a while, I'll be out of equilibrium, right?
I don't think so.
If you change the velocity field, then for a while you'll be out of equilibrium, and you're going to approach a new equilibrium, I guess.
Just I mean, the point is that the velocity field will be changing with time.
Mm-hmm.
But the continuity equation for psi squared would have that velocity field in it. And the continuity equation for the density would have that same velocity field in it. So the velocity field is changing with time, but as long as you've got the same velocity field in both continuity equations.
They're changing
I mean, it's a nice
together.
thought, Off
Okay.
the top of my head, I don't see it's going to make any difference actually.
Okay. Okay. Okay,
But yeah,
thanks.
nice try. I mean, I've
No, I'll continue.
been
I'll continue
dreaming
trying.
for 30 years of a way of creating on it. You know,
Thanks.
Okay, so more questions? Just only one remark
please.
about the nomological status of the wave function.
Yeah.
If you find some boundary condition which selects one
Yes.
one solution, then you'll be okay, right?
Yes. So there is
no boundary
there is an
condition.
idea that possibly in quantum gravity there might be a version of it in which the solution of the Wheeler-DeWitt equation is unique, and there's just this one. Then, if there's no contingency, I think then you could maybe have an argument for saying that it has a law-like structure rather than a thing-like status. But at the moment, there's no such theory.
Okay, okay. Okay.
All right.
That's it.
All right. Okay, Nelson.